Until I was in 6th grade, New York City, but not like Manhattan or Brooklyn. It was Queens. All right, so we're moving on to 3.5 only had how to do those trig derivatives, okay? So we have to remember sine and cosine. We threw the other 4 on the board. We talked about how we could get the other 4 with the quotient rule. As you start using them a bunch, and we will use them a bunch in examples today, you may just end up remembering them. There was that pattern, but we'll get a whole bunch of practice now with those trig derivatives now that we know the trig derivatives. All right? Yes. So we're not going to dwell on memorizing them, but we just need to practice a lot with them. We're skipping 3.6 for now. 3.6 is kind of an application section, and we're going to have a lab on 3.6 later that we do together. We're just going to jump to 3.7, which is the chain rule, and it's our third special rule for doing derivatives for when we have composite functions. So we've done product rule and quotient rule, and that's how we take derivatives when we have 2 functions of x being multiplied together, or when we have 2 functions of x being divided. And then our last special derivative rule is what to do when we have 1 function of x plugged inside of another function, which is a composition. Okay? So that's what we're going to talk about in 3.7. So these notes will be available on our Moodle page, and the video will be available as well. It's still good to take notes to make you pay attention as we're going, so you don't zone out. We'll also still do lots of examples. I'll still have lots of examples for you to do as well, but the notes will be available for you to reference back to and stuff. So. I haven't done this in a while. Not what I wanted to do. So this is when we've got one function plugged into another function. And we want the derivative. Or it's when we have a function of x, and then there is another operation being applied to it, like a power or a root or a trig function. So there's the blue g of x on the inside, which is a function of itself that we know how to find the derivative of, like with power rule or something. But then there's also this other operation enclosing it that would also have its own derivative rule. So that we've got the red and we've got the blue, and they have their own derivative rules, and one is embedded in the other. It's not multiplication, it's not division, it's composition. So the way that we do these derivatives is we always start with the derivative of the outside operation. So we're going to take the derivative of the f function, and we're going to leave g alone. So we're going to say this is f prime with original g. Just do However you would do the derivative of that outside operation, no matter what it is, whether it's a power or a trig function or whatever. The derivative of the outside with the regular g still on the inside. Regular g still untouched. And then you multiply that by g prime. So we like to say derivative of the outside times the derivative of the inside. So that the outside operation might be a power, it might be a trig function. Very shortly, we're going to learn more about exponentials, and we're going to learn about logarithms. Those are common functions for the f function. So we would apply first whatever the derivative rule is for the f function, and we leave the g alone completely. And then we would then multiply by whatever the derivative for the g function is. So it ends up being two things multiplied together in our answer. It's kind of low, isn't it? I was trying to keep the rule there, but I'll have it written down. So it's asking us to find the derivative for x squared minus 5x to the fourth power. So x squared minus 5x to the fourth power is a composite function. Inside the parentheses, we've got x squared minus 5x. We know how to find the derivative of that. That's just a polynomial that we would do power rule on each piece. But that's not the only thing there. We also have all of that stuff enclosed in a fourth power. So that's a composite function. Now, a few sections ago, we said we would have to FOIL that out and get it all written out term by term. Well, as that power on the outside gets bigger and bigger, that process is going to take longer and longer and longer to get that FOILed out. So if that was a 10th power, we wouldn't want to waste all that time in getting that FOILed out. So the chain rule would be much quicker. So our outside operation is the fourth power. And our inside operation, or our inside function, is the x squared minus 5x. And almost always you'll see some sort of math enclosure to help you decide what's outside and what's inside. A lot of times it's parentheses, but sometimes it's a square root can help us decide outside, inside, or a cubed root. Some of the trickiest ones are with exponentials, because you won't see an enclosure. So we'll talk about those when we get to those in a couple of sections. But a lot of times you're going to look for parentheses to help you decide what's inside and what's outside. So with chain rule, we always start with the derivative of the outside. And the outside is a fourth power. So how do we do derivatives of powers? The way we do derivatives of powers is we bring the power to the front, And with chain rule, we leave the inside stuff alone on this first step. Okay, we're just doing derivative of the fourth power. So bringing the 4 down, the inside stuff stays exactly the same. We'll deal with that in a minute. And the new power is 1 smaller. So we've taken care of the derivative for the fourth power. Old power out front, new power is 1 smaller. And then we also need to multiply by the derivative of what's inside. So now we'll take care of the x squared minus 5x. And to do the derivative of that, we just do the power rule for each piece. What's the derivative for x squared minus 5x? 2x minus 5. How we write this as our final answer is completely up to you. What we have written right now is perfectly fine. A lot of times if there's something with a power, they usually like to write it at the back. It really doesn't matter. Yeah, we could go ahead and distribute the 4 into the 2x minus 5. Could we distribute the 4 into the x squared minus 5x? We can't because it's got a cube on it. And order of operations say you have to do powers before multiplication. So unless you want to FOIL out that x squared minus 5x cubed, you leave that piece alone. So we could, if we wanted to, go ahead and say this is 8x minus 20 times x squared minus 5x cubed. There isn't really much more we can do with that unless we want to start FOILing things out. Okay, so derivative of the outside function times the derivative of the inside function.
So now we would have to use the product rule.
If we wanted to do second derivative, we would now do product rule because now we've got 2 functions of x being multiplied together. Product rule and chain rule. Mm-hmm.
So with the composite functions, is that the f of g function as well?
Yeah. Yeah, so this thing started off looking like this, f of g.
Okay, but that can also be written f circle, right?
Yes.
That's the same thing? Okay.
Yes.
Sure.
Mm-hmm. Yeah, this is the same thing as f composed of g of x. Yep. F composed of g is the same as f of g. Yep. Yep, those two guys are the same thing. Questions so far? Individually, these rules aren't too bad, but like Sunny was saying, when you start having to use like 2 or 3 rules at once in the same problem is when it really starts to get tricky. We're going to find the derivative for the square root of 5x plus 3. So this expression has an inside and an outside. It's got an inside and an outside. So if you want to, you can start by rewriting it. We're not doing the derivative yet, but we're just going to rewrite it so it's easier to see what the inside and the outside are. If we rewrite it, what is the outside going to be? A square root, right? How could we rewrite the square root so that it's easier to do a derivative? A 1/2 power. So we could rewrite this as 5x plus 3 to the 1/2 power. And then it's easier to see that the outside is a 1/2 power. We're going to have to do power rule to start with. And then we'll multiply by the derivative of the inside stuff. When you do your derivative of your outside, you leave your inside alone. So we're going to start with the derivative of anything that's to the 1/2 power. We bring our half out front, rewrite your base. New power is 1 less. And then change rule says we would also have to multiply by the derivative of the inside stuff, which is going to be a 5. Yep. And we'll clean this guy up a little bit. That negative 1/2 power means he's going to go to the bottom under a square root. So we're going to make a fraction. The 1/2, the 2 is also going to go to the bottom, but the 5 is going to stay in the top. The 5 doesn't have a negative power. So the 5 stays in the top. The 2 from the half, that's in the denominator, so that goes down. And that 5x plus 3 to the negative half means square root in the bottom as well. This one you could, since the derivative was just a number. We could put the 5 and the half together, just say we've got a coefficient of 5 halves. If we needed the second derivative, it would just be another chain rule. 5 halves, and then times a negative half. And then the same base, negative 3 halves, and then another 5. The derivative of cosine to the 9th of x. So shorthand notation for powers of trig, so that we don't have to use parentheses, is we typically write the powers in between the trig function and the angle. That's just because mathematicians are lazy and we don't like to write extra characters. This is really just cosine of x to the 9th power. We don't want to write it behind the x because it might get confused as to whether the entire cosine value is to the 9th power or just the angle is to the 9th power. And to distinguish, we would have to put parentheses. So distinguish between the two, we usually just put, if we want the whole thing to the ninth power, we put it on the cosine. So this is the entire cosine function to the ninth power. So what this means, if you want to rewrite it, this is cosine x. The whole thing is to the ninth power. That's what that means. So anytime you see the power between the trig and the angle, it means the whole thing is to that power. It means we're just being lazy and trying to not have to write parentheses. So it is a composite. Cosine has its own derivative rules, ninth power has its own derivative rules. One is plugged into the other. So to find the derivative, we're going to start with the derivative of the outside. So with old power out front, rewrite your same exact base. New power is one smaller. And then multiplied by the derivative of the inside stuff. And the derivative for cosine is negative sine. Sine and cosine just go back and forth between each other. And remember, anything that starts with a C is negative. Derivative is negative. All the trig functions that start with a C, their derivatives are negative. Cosine, cosecant, cotangent, all their derivatives are negative. That negative is like a coefficient of -1. We should move it to the front. So this is like -9 cosine to the 8th times sine. Really doesn't matter the order that you put the sine and the cosine in. Again, we typically write things with powers at the end, but that doesn't matter. It's not going to make a difference in the answer. So you might have to look back at your trig derivatives for this. We haven't had much or any practice with our trig derivatives yet. If we want the derivative for tangent cubed. So we did our trig derivatives on Thursday. That would be the derivative of our inside, and then we also need the derivative of our outside. What do we get for the derivative of the, the outside function? 3 tan squared x, yep. The 3 comes out because the outside is the cubed part. So old power comes out, you rewrite your base, new power is 1 smaller. And then we also have to multiply by the derivative of the base. So we're gonna multiply by the derivative of tan, which is what? Secant squared. So we get 3 times tan squared times secant squared. And there isn't anything we can do with that. That's it. If we wanted to take that derivative, we would need product rules and chain rules on both of them. Yes.
That's what it is.
Yes. Does anybody plan on anybody gonna do engineering? You're gonna take differential equations and you will have problems that take multiple pages. They're fun. They're not difficult problems, they're just take a long time. Just a lot of work to do. It's such a good feeling though when you get to the end of the problem and you have it right and you've got like 3 pages of work and yes.
I don't See, the only reason why I'm taking this is because I gotta take physics.
Mm-hmm.
Just too much, see why I need to. I figured I would take more science.
Math. See, a lot of people don't understand just because they're so resistant to the math. Most of what college math does is just help you to think logically and exercise your brain. It's not actually the content of the class. For most people, the content of the class is garbage. And I'll be happy to admit that.
We're never gonna use box and whisker charts?
You're never going to use box and whisker charts again in the rest of your life.
I'm not gonna use.
You actually might. If you ever read any humanities, social science papers, they might use box and whisker charts to display data.
My advisor, he claims to say I'm gonna need this class to write out prescriptions and stuff like that.
Yeah.
I'm sitting here, I'm like.
Because you gotta make sure you don't overdose somebody.
That's
yeah,
algebra.
I don't think I need all this. I don't think I need all this math.
It's more to exercise your brain and help you to think logically and problem solve and work through steps and.
Unless you want to do that.
You do need statistics though,
Yeah, I know that.
because you're gonna have to be able to say this, you have a certain percent chance of this, plus a certain percent chance of this, so you have a certain percent chance of that.
Does anybody have any questions yet on chain rule? No? Explanation with the composite?
More sense
The composite?
than what I got in high school.
Good.
Just gotta do this, guys.
Yeah, no, you're right.
And they give you fill-in notes, and you just copy from the
Wait,
board.
they
You
give
have
you
no
that?
idea what you're talking about.
Then again, I took it home. Did it myself. It wasn't too bad. You just kind of learned to watch your little bird.
X plus 5 over x squared minus 3, and the whole thing is squared.
It's gonna be a quotient rule inside of a chain rule.
It is a quotient rule inside of a chain rule. But the first thing we're going to see is that there's an inside function and there's an outside function. Okay? So don't worry about the quotient rule yet. If we see there's an inside and an outside, we do the chain rule. There's an inside and there's an outside, so we start with the chain rule. And the chain rule says do the derivative of the outside first. So again, don't worry about the quotient rule yet. The quotient rule is just the inside piece, so we'll worry about that when we get to the inside. The outside is just a square. So the 2 comes out front. We just rewrite the inside stuff. Oops. New power is 1 smaller. You don't have to write a power of 1, but when I rewrite my final answer, I'm probably not going to write it. I'm not going to write it. So that's the derivative of the outside. That's how we do the derivative of a square. That's our power rule. And now we need to multiply by the derivative of the inside. The inside is a quotient. So now we'll do our quotient rule. So with quotient rule, we start with the derivative of which one? Start with the derivative of the top. The derivative of x plus 5 is just 1. And you pair it up with original of the bottom. Remember, you do mix and match. And does quotient rule have a plus or a minus? It's got a minus. And then flip-flop. First one had derivative of top, original bottom, so now flip-flop. Original top, derivative of bottom. All over
X squared minus 9 squared.
Bottom squared. So we can clean up that numerator a little bit. They don't, because that's subtraction. So we've got x squared minus 3, because it's just being multiplied by 1. Here, I need to distribute that 2x. And I need to distribute the minus. So that's minus 2x squared and minus 10x. And then we can combine some like terms. And we almost got our answer. I'm going to rewrite this one more time. Since it's all multiplication, I'm just going to put it all in one fraction. Especially since our denominators have the same factor in them. I can just say I've got a cubed in the denominator. That might make it look a little nicer. None of this is actually making the derivative any different. We technically had the derivative right here. We're just trying to clean it up a little bit. So we've got, I'm just gonna say one fraction, 2x plus 5, negative x squared minus 10x minus 3. And I've got a total of 3 x squared minus 3's in the bottom. And we could even pull the negative out of that trinomial if we wanted to and say -2 and make it all positive back there. I mean, there's no, like we've said before, there's no telling on when to stop. Go ahead.
At the top,
Here.
does x squared minus 3 not cancel out and then just 1 x squared minus 3?
It doesn't because it's not in factored form right now. Because of this minus right here, we can't cancel. We can only cancel between the top and the bottom if it's factored. So if this was x squared minus 3 times something, then we could cancel. If it was x squared minus 3 times -2x squared minus 10x over x squared minus 3, then we could cancel. So if it's in factored form, we're allowed to cancel because multiplication and division will cancel each other out. But this is subtraction and division. Yeah. The addition and subtraction kind of glues all that stuff together and we're not allowed to cancel. So that one requires a couple rules together. Oh, you want to do second derivative on that?
No.
That would be,
You are the one person I would suggest that.
well, I don't think it would be that
Wait, you
bad.
could simplify the top out pretty well, so it would just be a chain rule.
It would be a quotient rule, a product rule, and a chain rule.
You could simplify.
Well,
the
you would
product
just
rule
do,
out.
it wouldn't be that bad.
It wouldn't be that bad, but it'd be a quotient
It would
rule,
just
a
be
product rule, and a chain rule.
product rule, it would be.
It would start as a
quotient
quotient.
rule with the product rule to get the first one.
You do a product for the derivative of the top
You don't really need.
and a chain for the derivative of the bottom.
And then under the bottom, it would be x squared minus 3.
I'd probably FOIL out the top since there's no.
I was gonna do
I don't
that,
know.
my brain said no. Like, I've got the bottom 4 out. Where it was squared. Now two more forwards.
Why what? I don't hate you. I actually like you guys very much.
Okay, so you just make this one. How do I do? Thank you.
We're going to find the equation of the tangent line to the graph of the function f of x equals 1/3 x times the square root of x squared plus 5 at the point 2, 2. We've got to do a product rule and a chain rule. Why do we have to do derivative at all? We need slope in order to write the equation of a line, a tangent line, okay? Our ultimate goal here is to have an equation of a tangent line. Our final answer is going to be an equation of a line. We want that line to be tangent to this graph. In order to be tangent to this graph, we need to know what the slope of that graph is at 2, 2. And the way that we do slope of a graph is derivative. Okay, so we can start off with f prime of x. Only a piece of this function is a composite. Only a piece of it. So don't start with chain rule. We're starting with product rule. Overall, this function is a product of several things. It's several things multiplied together, and just one of those things is a composite. So sometimes when you know you've got to use several rules, it's hard to decide what rule to start with. You know you're going to do product rule and chain rule, but you don't know which one to start with. So look and see what pieces that's hard trying to think of a way to say this. Overall, this function is not a composite. It's not overall an inside and an outside. Just a piece of it is an inside and an outside. Just that one last piece has an inside outside.
G of x and h of x.
Mm-hmm.
Or 1/3 x, would that x go from the top or the bottom?
1/3 x.
The x, does the x have a negative power? Then it would go to the top. So we're going to start with f prime. That's going to give us our slope. And when there's coefficients, I like to group it in with one of my pieces. You don't have to do that. You can ignore it and just throw it in your final answer. Sometimes that's not safe though. Some people forget to do it, or some people forget to distribute it to everything so that it doesn't get forgotten. I like to go ahead and forget to get forgotten. Is that what I just said?
Yeah, you said that. Yeah, it's okay.
I've lived in North Carolina too long. I want to think of the entire f as a product of two functions. So I'm going to think of my first function as 1/3 x, and my second function as square root x squared plus 5. So f is a product of two functions. No matter what they look like, f is a product of two functions. So I'm going to start with my product rule. And when I get to the point where I need the derivative of the second piece, then I'll do my chain rule. So what's the derivative of the first piece? It's just 1/3, because it's a linear function. It has a power of 1. If you want, you can do the power rule on it. But you're bringing out a 1, new power is 0. So the shortcut with those linear functions is the derivative is just the coefficient. So the derivative of our first piece is 1/3, and we match that up with the original of the second piece. And then product rule has a plus or a minus? Plus. And then we flip-flop. We'll do the original of the first, the derivative of the second, and this is the only part where we need the chain rule, because we now want the derivative of the second piece. So think of this as x squared plus 5 to the half. So the derivative is going to be 1/2 x squared plus 5 to the negative half. That takes care of the outside part. And then times 2x will take care of the inside part. So just do this one piece at a time, one small piece at a time. So this is derivative, original. And then we did original. And then all of this stuff here is derivative of the second with chain rule. Now you don't have to do much to clean this up because we're plugging a number in. It's going to be a whole lot easier to simplify this with a number in there. We only need the slope at x equals 2. So you don't have to waste a whole lot of time and accidentally make an algebra mistake trying to mess around with simplifying with the x's in there. We have our derivative. We want the slope at 2. So you can go straight right now to saying, all right, what is f prime at 2? We've done the derivative. We haven't cleaned it up. We don't necessarily need to clean it up, and it might be easier to clean it up with numbers in it. So we've got a third times the square root of 2 squared plus 5 plus a third times 2 times a half times 2 squared plus 5 to the negative half times 2 times 2. I don't think it's a good idea to type that whole thing in your calculator at once. You might be able to. Just be careful. What does that first term come out to be? All of it together, yeah, comes out to be 1. Because 2 squared is 4, 4 plus 5 is 9, square root of 9 is 3, 3 times a third is 1. So all of this together is 1. Two times a third is 2/3. And then we have a half. Yep, this guy here is 1/3. And that is 4. So we get 4/9. So 1 plus 4/9. Did you plug the whole thing in at once?
Yeah,
No,
but yeah,
I
I put it
had
all in at
mine
once and
simple.
it came out correct.
Good.
Before I did that,
simplified
I
it.
had mine simplified to square root of x squared plus 5 over 3 plus x squared over 3 square root of x squared minus 5.
It would be 2x
And I ended
squared.
up with 1 minus 4/3.
I simplified it that far too. It would be 2, the second part would be 2x squared over 6 square root of 2x plus 5.
Yes.
Because you have a 1/3 and a 2 that you need to multiply into that fraction. You got a 1/3 x
Well,
and 2x.
I've got 1/3 x. No, I've got 1/3 x times x over the square root of x squared minus
The
5.
2 and the half can cancel.
The 2.5 would cancel.
Yeah, this half and this 2 could cancel.
And that would just leave x.
So you have a 2 in the top,
Squared. Yeah.
but you are going to have an x squared in the top. Because there's an x here and there's an x here. So you should have x squared over 3 times the square root of x squared plus 5.
I had x squared minus 5. So it's gonna be 34 over 9.
So now we've got a slope and a point. We want to write the equation for our tangent line. We've got a slope of 13/9, and we've got a point of 2, which was given to us. So you can use slope-intercept form, you can use point-slope form. We want our final answer as y equals mx plus b, but if you like point-slope form to set it up, then that's perfectly fine. I don't like sitting here. So now write out the equation for your line. And y equals mx plus b, so you've got your m and your b now. Should be negative. Subtract it over genetic. Yep. So then you've got your m and your b. So right, y equals mx plus b, your m and your b.
Alex, you had something the same way I did.
Very similarly, so I don't know what you did wrong.
I had one sign off.
You have one sign wrong?
I had a close one.
Okay.
Is it just me, or is it like a whole lot simpler than I had it simplified like that?
It is when you just put it all in at once and got it.
No, I did mine in my head, because I had, x squared plus 5, and put it 2 in.
Those guys are gonna be switched.
So I'm coming off of 36, 37 hours of 2 days. I'm not doing anything in my head. It's not.
I did the high school thing where you simplify down so far, and it's just like one term.
I don't think you can do that with this
You got
unless
it.
you want to
Sorry.
multiply by some LC or L.
Because to me, right, you plug in
So
that
I've
four,
got
you get
LCF.
square root out of 3, which is over there. And then
Never really
you
don't like
get
that.
4 over square root. That will just make it.
It simplifies a lot faster that way. I just suggested plugging it in up there because I've just seen a lot in the past of people making the algebra simplification mistakes. Where if they would have plugged it in earlier, they would have gotten it. But when they try to do algebra simplification, they simplify wrong, and then they get the wrong answer. Just because they simplified wrong.
See, I like it. I just hate logarithms.
I don't mind trick. I hate logarithms.
I hate it.
I find certain aspects.
The algebra
'Cause-
or the calculus?
Both.
I hate trigs and logarithms because it's a lot. It's more memorization stuff.
I just
Because
forget.
I'm better with
It's
things
just
that
one
you.
more
I'm better with,
calculus rule.
but I'm better with things that you can work out, and figure out how to
You can't
do
work
it
those
versus things you have to memorize.
All you gotta do is graph them and then look at the derivative and make a derivative and then take the function from the derivative.
No. Yeah.
Does anybody need help with their equation?
But thank you.
Getting our down.
I have taken your suggestion into consideration and I will,
What did we get for B?
negative 8.8 over 9.
Negative 8 over 9? Yep.
I almost said 8.7.
So we already know our slope is 13/9. We should get a B value of negative 8/9. That means our equation is y equals 13/9. Y equals 13/9 x what? You still- minus 8/9. So that's the equation for our tangent line. So I know one thing that on your homework, they like to ask you to do.
Okay, so no,
Let me see here. Let me see if I could do something fancy.
Like what?
Like open up Desmos.
Oh, just hit
Is there
Edge.
I don't like Edge.
Well, then go to Chrome. Go to Chrome. You have Chrome download, don't you?
Click on photos.
Do you see it?
Yeah, hit
Use
the,
Internet Explorer.
hit the three, hit
There's
the
the
little
real
lines
internet
and the
browser,
little
Internet
boxes next to
Explorer.
it.
That's a lie. Get out of here, Mr. Bing.
And then you can find Chrome. Internet Explorer no longer exists.
What's that?
It's still there,
It's
unfortunately.
Microsoft Edge.
What's the name? Oh yeah.
No, it was there, it was right there.
No, that was Edge.
No, it was Edge, and then there was Internet Explorer.
That's the way you can open Internet Explorer.
Yeah, Internet Explorer's still in there somewhere.
It's
Yeah, I don't use
The
Said it
only
was
time
gone.
I ever see Internet Explorer is like when I'm deep in the settings and click on something. that
Exactly.
opens up the website. That's the only.
One of those settings they've never changed.
Yeah. But see, Edge is supposed to be a whole lot more like Chrome and
I'll use
Firefox, but it's just like too late.
Well, I mean, like,
Edge.
Edge is pretty good. The only problem I had with it was no extensions. I want to use my ad blocker and whatnot.
Yeah, that was
I don't use that.
See, I just use Chrome for all that.
I'm just gonna graph these two real quick next to each other and we're gonna have a break.
Go ahead.
Safari.
X squared plus 5.
I don't use Edge. It's only a
Yeah,
matter
they
of
use
finding the
Safari.
recording.
That's about it.
Talking about.
Haven't used Internet Explorer in years.
So there's our 1/3 x times the square root of x squared plus 5 graph, and I'll adjust it here in just a second. And then our tangent line we said was y equals 13/9 x minus 8/9.
Oh boy, here we go.
Boy.
Oh boy. Look at you.
Isn't that beautiful?
It's like a half
So there's our 2, 2 right there.
If you make the first line blue and the second line red, that's exactly what it looks like.
Okay, so.
So there's 2, 2.
Person.
Yep. The red graph is our function. The blue graph is our tangent line. It's tangent because it's coming in and it's touching at just that exact one spot. If we were to zoom in, those two are nearly indistinguishable from one another. They've got the exact same slope.
Looks like it's making a whole line.
Mm-hmm. Yep. They've got the exact same slope right there. Yep. So Desmos is much more user-friendly. You don't have to go through all those crazy menus on your calculator, and you really could just literally use your mouse and touch points on the graph, and the point will pop up where, like, if you want to find a maximum or a minimum or a value on your calculator, you have to go to the calc menu and say find the max and do a left bound, a right bound, and a guess and all that mess here. So if I want to find where they touch, I literally just touch the screen and it tells me 2, 2. All right, it's not working anymore. Never mind. It does. It's so much more user friendly. It's so much more user friendly. Desmos.com.
It's really user friendly.
I love it.
Actually graph
It's the
the
app
circle.
on.
Mm-hmm.
That
Love
was
it.
how I found it. I was like, how do you, I want to graph the graphs.
And like zooming in and zooming out, like on your calculator, to zoom in and zoom out and adjusting your window can be a real pain in the butt. And this one is so much nicer to zoom in and zoom out. It's got the zoom in and zoom out up there in the corner. And like I think you can even just drag like with your mouse to zoom in and zoom out and figure out like the points you're looking for. So if you've never played with Desmos, it's just a free website. If I've got the option, I'll use it 9 times out of 10 before I'll use my graphing calculator.
If you create an account, what does that do?
It lets you save things. It lets you save these graphs and like export them as like picture files and stuff. Some teachers can create like labs and create and write code in Desmos.
See,
What?
those things just like,
Hmm?
just
You can write code.
You can write code.
They got that, they can get that.
You ain't good enough, code breaker.
Man, I won't be sitting there trying to put in the codes.
All right, it's definitely, it's 11 o'clock is break time.
Oh, wow.
Yes.
Anybody else pretty good yet? I was not gonna put that some chips.
Oreos, time for the Oreos.
I know, why does it hurt so much? It's not gonna be want that one. Oh, look dirty. I'm supposed to be young.